For over a century and a half, the southern San Andreas Fault has stayed eerily silent, locked tight since the magnitude 7.9 shock of 1857. Yet beneath today's calm, GPS sensors reveal nearly 3 meters of hidden strain, straining for release. Why has this segment stayed quiet so long? And just how close are we to a catastrophic breakthrough? On the morning of January 9, 1857, the ground along the southern San Andreas Fault broke open in a way no one alive had ever seen. Over the course of just a few minutes, a rupture raced nearly 360 kilometers from Parkfield in the north to the Cajon Pass near San Bernardino. The earthquake reached a moment magnitude of 7.9, making it the largest quake ever recorded in Southern California. Along the fault trace, the earth shifted sideways by an average of 4.5 meters, enough to tear fences apart and leave deep scars across the landscape. In some places, the offset peaked at nearly 9 meters. Shaking was violent near Fort Tejon, where the ground moved so fiercely that the Kern River briefly reversed its flow, and Tulare Lake spilled onto its banks. Los Angeles, still a small town at the time, felt strong tremors, but was spared the worst. Aftershocks rattled the region for years, including several above magnitude 6. The 1857 rupture stands as a benchmark, a rare full-length event that released centuries of built-up strain in a single catastrophic moment. Today, scientists use these numbers, magnitude, rupture length, and slip, as the baseline for understanding what the southern San Andreas is capable of when it finally gives way. Across Southern California, a network of GPS stations quietly records the ground's every move. These instruments, spaced 10 to 20 kilometers apart, detect shifts as small as a few millimeters per year, far below what anyone could feel. Over decades, however, those tiny motions add up. What they reveal is a band of strain running along the southern San Andreas Fault, a zone where the Earth's crust is being steadily pulled and compressed, but not slipping to relieve the pressure. Scientists call this a locked fault segment. Here, the plates on either side of the fault are stuck together down to depths of 15 to 25 kilometers. Above this locking depth, the rocks flex and store energy like a giant spring. The GPS data show a consistent pattern. The Pacific Plate is trying to slide northwest at about 46 millimeters per year, but the fault itself barely budges. Instead, the difference between the expected motion and the actual slip, the slip deficit, keeps growing. Strain rate maps built from 30 years of continuous GPS measurements highlight a concentrated band of shear strain, about 8 times 10 to the -6 per year, centered on the fault. When multiplied by the time since the last major quake, the numbers become striking. The southern segment has accumulated a slip deficit of roughly 2.8 meters since 1857. That is almost the same amount of movement released in the last big event. Dr. Jennifer McGill, a geodesy expert with UNAVCO, explains that our GPS network records a few millimeters of motion each year, and over a century that adds up to a multi-meter fault slip. All this hidden strain sits locked beneath the surface, waiting for the fault to catch up. Earthquake science relies on 3 main families of models: dynamic, kinematic, and hybrid. Each starts with the same foundation: precise maps of fault geometry, locking depth, and the slow buildup of strain deep underground. Dynamic rupture models, such as SPEC-FEAM M3D and RSQSM, simulate earthquakes from the ground up. They solve the equations that govern how stress and friction interact, following the rupture from its first break to its final slip. Friction laws, rate and state or slip weakening, shape how the fault resists motion and how quickly it gives way. The outcome is shaped not just by the amount of stored strain, but by the fault's bends, roughness, and the way energy moves along the rupture front. Sometimes a small change in geometry or energy flux can decide whether a rupture stops or leaps to another segment. Kinematic models take a different approach. They use observed or assumed slip patterns to replay past earthquakes or test what might happen if slip is released in a certain way. These models are fast and flexible, making them essential for hazard mapping and risk assessments such as UCERF3 and UCERF4. Hybrid ensembles combine the strengths of both. By running thousands of randomized scenarios, they capture a wide range of possible ruptures and ground motions. All three model types depend on GPS and INSAR data to set their starting conditions: accumulated slip deficit, estimated locking depth, and the current stress field. As Professor Robin Abraham of the Southern California Earthquake Center Dynamic Rupture Group puts it, the physics encoded in these models can decide whether a fault breaks as a single block or jumps across the transverse ranges. This suite of models anchors the earthquake scenarios to come, rooting each forecast in the best available science. 3 earthquake scenarios stand out in the latest rupture models, each with its own signature of ground motion and energy release. The first, a southern segment-only rupture, tracks the fault from the Tejon Hills south to the Salton Sea. Models show this pathway could deliver peak ground accelerations of up to 0.8 G in the Los Angeles basin, with shaking intensities reaching the upper end of the modified Mercalli scale, enough to jolt even reinforced structures. The frequency content here is broad, but the most damaging energy clusters in the 1 to 5 Hz range, which happens to match the natural resonance of many mid-rise buildings. In this scenario, nearly all of the accumulated slip deficit, close to 4 meters on average, is released in a violent burst along the fault's locked core. A second scenario, the multi-segment rupture, allows the earthquake to leap across the transverse ranges, extending the break into the Coachella and Imperial valleys. This jump injects more high-frequency shaking into the mix, sending sharp, rapid jolts through soils and infrastructure. The shaking footprint expands, with strong motion stretching well beyond the Los Angeles basin. Peak accelerations remain high, but the spectrum shifts upward, with more energy arriving in frequencies above 5 Hz, which can be especially punishing for short structures and lifeline systems like pipelines and rail lines. The third scenario, partial slip release, tells a different story. Here, only about 60% of the slip deficit is unleashed on the main San Andreas, while adjacent faults take up the rest. The result is a wider area of moderate shaking, with peak accelerations closer to 0.4 G, but less concentrated destruction. The frequency content is more muted, with energy spread out over a longer duration. This kind of event can still trigger landslides and liquefaction, but the risk of catastrophic building collapse drops. Each scenario paints a distinct picture of how the fault's hidden strain might translate into surface shaking, and each would leave a unique imprint on Southern California's landscape. Hazard models translate all the slip deficit and strain measurements into ODDS, numbers that help frame the risk, even if they can't predict the exact day the fault will break. According to the Uniform California Earthquake Rupture Forecast, the chance of a magnitude 7 or greater earthquake on the southern San Andreas in the next 10 years sits at about 4%. Over a century, that probability rises to roughly 15% in the baseline model. When the elapsed time since the last major quake is factored in, accounting for the 168 years of strain now stored along the fault, the ODDS reach as high as 22% over the next 100 years. Dr. Emily O'Neill, a hazard analyst with the USGS, explains that these percentages reflect both the best available science and the real uncertainties in how the fault behaves. The numbers are not a countdown. They are a measure of how much strain has built up and how sensitive the forecasts are to new data and model choices. The risk maps for the southern San Andreas Fault draw a clear boundary across Southern California. Communities in the Inland Empire, the Coachella Valley, and the Antelope Valley sit squarely in the highest shaking zones for nearly every rupture scenario. The Los Angeles Basin, with its dense population and layered infrastructure, faces strong ground motion, especially where soft soils amplify shaking. Lifelines cross the fault at critical points. Interstate 5 and Interstate 405 thread through the San Fernando Valley, while water aqueducts and power transmission corridors cross near Cajon Pass and the San Gorgonio Pass. These are not just lines on a map. They are the arteries that keep the region running. Ms. Ana Lopez, a lifeline engineer for Los Angeles County, puts it plainly. Our pipelines sit on a fault that has been silent for over a century. The hidden strain could shear joints by several centimeters. For every region in the shaking footprint, the question is not just about probability, but about how ready these lifelines are to withstand the next break. Today, over 20 million Californians live atop a fault storing centuries of strain, tracked in real time but not controlled. As cities expand and infrastructure ages, the clock keeps ticking. Nature sets the deadline. Preparation sets the outcome. The real question is, will readiness outpace inevitability? Share your thoughts below.